In May 2026, astronomers announced a discovery that seemed to provide a major breakthrough in the search for alien life. They had detected a magnetic field on Proxima Centauri D, a rocky planet orbiting the star closest to our Sun. This enthusiasm is built on the baseline of our own experience. Earth's magnetic field is a protective bubble that deflects a constant stream of charged particles from the Sun. It is the primary reason our atmosphere hasn't been stripped away into space. We know the stakes of losing this shield because we see the results on Mars. When the Martian dynamo died and its magnetic field collapsed, the solar wind eroded its atmosphere, leaving behind a cold, irradiated desert. Finding a magnetic field on a rocky exoplanet should be a major victory for habitability. But the May 2026 paper describes a different process than what the headlines suggested. The researchers did not photograph a protective magnetosphere around Proxima D. They inferred the field's existence by watching the host star. Proxima Centauri spits out high-energy flares on a precise 5-day rhythm. That timing perfectly matches the 5-day orbit of Proxima D as it sweeps around the star. In this system, the planet's magnetic field acts like a conductive wire, tethering the world directly to its star. The two are phase-locked, which means the star's activity is reacting to the planet's movement. That 5-day rhythm suggests the planet is caught in a loop. In this environment, a magnetic field might be the very thing that connects a world to its own bombardment. This chart shows the extreme difference in scale between our solar system and Proxima Centauri. Earth sits 150 million kilometers from a relatively quiet sun. Proxima D orbits at a tightly compressed 4.3 million kilometers from a star that is highly volatile. At this distance, the planet undergoes subalfvénic interaction. Proxima D is orbiting entirely inside the region dominated by the star's own magnetic field. It isn't sitting behind a shield, it is sitting inside the star's magnetic environment. The environment is almost continuously flaring. Because Proxima D is so close, the particle flux it receives is thousands of times heavier than the bombardment Earth faces during a comparable solar event. While the 16 Gauss field on Proxima D is 30 times stronger than Earth's, that number doesn't account for the environment. The radiation it must withstand scales much faster than the strength of the field. If Earth's magnetic field were placed in this exact orbit, the intense stellar wind would strip it away in a cosmological blink. The physics of the system functions like a machine. As Proxima D's magnetic field moves through the star's environment, it acts as a giant conductor. This movement induces massive electrical currents. These currents travel along the connecting magnetic field lines, flowing backwards to deposit their energy directly onto the stellar surface. This sudden energy deposit triggers an intense stellar flare. That explosion fires a blast of radiation right back down the same magnetic pathway, directly at the planet. This cycle operates like a clock. Every 5 days, the planet's orbit closes the circuit and the star answers. The 16 Gauss measurement is the mathematical minimum required to explain why the star is reacting with such intensity. It is a calculation of how much energy the planet is feeding back into the star. The planet is an active participant in its own erosion. By maintaining a magnetic field in this orbit, it completes an electromagnetic circuit that ensures its atmosphere is pounded around the clock. Proxima Centauri is part of the most common class of stars. Red dwarfs make up roughly 75% of the Milky Way's population. These stars go through a violently hot pre-main sequence phase that lasts for over 100 million years. During this time, high-energy UV radiation would boil off early oceans and split water molecules, venting hydrogen into space long before life could emerge. Because these planets must orbit so close to stay warm, gravity tidally locks them. This halts their independent rotation, leaving one side to broil while the other side stays cold enough to freeze any remaining atmosphere into solid ice. This slow rotation weakens the planet's internal dynamo, degrading the magnetic field exactly when it is needed most to combat a star that will keep flaring for trillions of years. These factors suggest that the magnetic fields we are detecting now are likely guarding sterile corpses, worlds that lost their atmospheres billions of years ago. This poses a critical challenge for our search for life. Our next-generation telescopes are specifically looking at these red dwarf systems because they are the easiest targets to detect, despite the extreme hostility of the environment. This data points to a potential structural filter in the Milky Way. Even if habitable zones are crowded with planets, the physics inside them could be systematically stripping those worlds bare before life can even start. The May 2026 finding is a genuine scientific first, but the message it carries is sobering. Proxima Centauri is providing a physical warning about a galaxy that constantly, mechanically erodes its most common worlds.